Offshore operations function in some of the world's most demanding environments. Oil rigs, wind farms, and vessels such as FPSOs, SOVs, and floatals operate far from shore, where immediate and effective emergency response is vital. Isolation, unpredictable weather, and the complexity of marine structures create unique challenges that require specialized systems and equipment. Addressing these challenges depends on advanced offshore emergency response technologies, tools and strategies designed to detect incidents early, coordinate actions swiftly, and safeguard both personnel and assets under the most extreme conditions. Offshore operations face a wide spectrum of potential emergencies: fires, oil spills, equipment failures, medical incidents, and extreme weather among them. Their remote and isolated locations make response and rescue efforts complex, underscoring the importance of well-coordinated emergency management. The effectiveness and speed of the response often determine the extent of environmental, structural, and human impact. A structured emergency response framework governs offshore safety, built around 3 key stages: prevention, mitigation, and recovery. Prevention focuses on continuous monitoring and maintenance, supported by sensor networks, satellite communication links, and routine inspections that help detect irregularities before they escalate. When an incident occurs, mitigation becomes the priority. This involves activating emergency teams, deploying firefighting systems, and containing environmental threats such as oil spills through barriers and booms. The final stage, recovery, addresses restoration and improvement. Once the immediate danger is under control, efforts shift toward resuming operations, repairing damage, and analyzing root causes. Findings from these investigations drive procedural updates and technological enhancements that strengthen safety standards and resilience for future offshore missions. Response and rescue systems form the backbone of offshore emergency preparedness, ensuring that personnel have reliable means of evacuation and survival when crises occur. Among the most vital components are lifeboats and life rafts, both designed to safeguard crews during fires, structural failures, or extreme weather events. Lifeboats are rigid, motorized vessels built for rapid evacuation and equipped with essential supplies such as water, rations, and first aid kits. They are typically launched through gravity davits or free-fall systems, allowing deployment even in rough seas. Recent safety evaluations have highlighted a growing challenge. Around 36% of North Sea workers now exceed 100 kilograms, surpassing the standard design assumption for evacuation systems. According to the Health and Safety Executive, offshore operators are legally required to ensure escape and rescue systems account for current workforce characteristics, and the OUK has issued new industry guidance under review to address this concern. Life rafts, by contrast, offer a compact and flexible alternative. These inflatable systems can be automatically or manually deployed and are ideal for installations with limited space. Despite their smaller footprint, they accommodate multiple occupants and include survival gear, signaling tools, and protective canopies. Many are enhanced with thermal insulation and reflective materials to improve visibility and endurance in severe marine conditions. Together, lifeboats and life rafts form a critical safety line, technologies engineered to protect lives when offshore operations face their most unpredictable moments. In offshore operations, rapid detection and uninterrupted communication form the foundation of effective emergency response. These systems are critical for preventing incidents, minimizing risks, and ensuring a coordinated reaction when crises occur. Among the most advanced tools are real-time monitoring systems, which integrate networks of sensors and cameras to continuously observe the condition of equipment and the surrounding environment. These sensors track variables such as pressure, temperature, and structural integrity, sending data to analytic platforms where algorithms and machine learning models identify anomalies and predict failures. When irregularities are detected, automated alerts are dispatched to control rooms with precise location and issue details, enabling rapid and targeted intervention. Weather monitoring systems also play a decisive role. Equipped with radar, atmospheric sensors, and satellite data integration, they forecast severe conditions such as high winds or storms. This foresight allows operators to secure assets, prepare personnel, and plan safe evacuation windows, critical for both safety and operational continuity. Another essential element is real-time personnel tracking. Wearable devices linked to onboard communication systems transmit each crew member's position to a central hub, ensuring instant accountability during emergencies. By knowing the exact location of every individual, response teams can coordinate mustering and rescue operations with greater precision, drastically reducing evacuation times and the risk of oversight. Given the isolation of offshore environments, satellite communication provides a vital link between sea and shore. It ensures uninterrupted data transmission from monitoring systems and maintains connectivity even under severe conditions. Satellites also support telemedicine, enabling remote consultations and live transmission of medical data to onshore specialists when immediate assistance is required. Lastly, drones and remotely operated vehicles extend situational awareness and response capabilities. Drones perform aerial assessments, mapping incident areas without endangering personnel, while ROVs carry out underwater inspections, repairs, and leak containment. Together, these technologies create an integrated emergency response network, one that monitors, analyzes, and reacts across every dimension of offshore safety. Dynamic positioning uses advanced algorithms, sensors, and multiple thrusters to maintain a vessel's position with pinpoint accuracy, regardless of wind, waves, or current. This stability is critical during rescue missions, medical evacuations, or oil spill containment, where even minor drift could endanger personnel or compromise response efforts. Equipped with firefighting systems, medical treatment facilities, and fast response craft, SOVs serve as mobile command centers during emergencies. Their ability to remain on site for extended periods allows them to coordinate complex rescue and containment operations while housing emergency teams and technical specialists. Beyond crisis response, these vessels also support preventive maintenance of offshore structures, reducing the likelihood of incidents. Their cranes and motion-compensated gangways enable precise, safe operations without returning to port, ensuring continuity in both maintenance and emergency scenarios. Dynamic positioning is integrated with broader logistics and data management platforms, giving commanders a single interface that consolidates vessel status, environmental data, and crew information in real time. Geographic information system tools further enhance decision-making by mapping spill trajectories, asset locations, and personnel positions. This spatial intelligence enables fast, informed, and coordinated actions, making SOVs indispensable assets in maintaining offshore safety and operational resilience. Effective offshore emergency response depends on continuous training and simulation designed to prepare crews for a wide range of high-risk situations. Regular drills replicate potential incidents such as fires, oil spills, medical crises, and structural failures, ensuring that personnel can act quickly and cohesively under pressure. Advancements in virtual reality and augmented reality have transformed traditional training methods. These technologies create immersive, realistic environments that mirror the conditions of real offshore emergencies, allowing crews to practice decision-making, communication, and coordination in controlled yet lifelike scenarios. By combining technical accuracy with experiential learning, VR and AR simulations strengthen both individual competence and team readiness, key factors in achieving swift, effective responses when emergencies occur at sea. Despite major advancements in offshore emergency response, several challenges continue to shape its development. The high cost of implementation, the complex integration of diverse technologies, and the management of vast data streams all present ongoing obstacles. Ensuring seamless coordination between systems, ranging from monitoring networks to communication platforms, requires both technical expertise and substantial investment. Looking ahead, the focus is shifting toward greater automation and intelligence. The integration of artificial intelligence will enhance decision-making by analyzing real-time data and predicting the best course of action during emergencies. Autonomous drones are expected to take on faster and safer initial response roles, providing immediate visual assessment without endangering personnel. Meanwhile, advances in remotely operated vehicle technology will allow for more complex underwater repairs and inspections with higher precision. Together, these innovations will drive the next generation of offshore safety systems more connected, predictive, and resilient than ever before.